So our first speaker in this theatre is Sujit from Relics Group, where he's a technology research director at Elsevier Labs.
Yep.
And he helps build technology that helps scientists make breakthroughs and clinicians, that's a hard word to say, clinicians save lives. And his interests are information retrieval, ontologies, NLP, machine learning, deep learning, distributed processing. And his talk today will be on learning a joint embedding representation for image search using self-supervised means. So, Sujit,
Right.
to you.
Thank you, Charlie. And thanks to everyone who, all of you who came in. So today, as the title says, I'm going to talk about learning a joint embedding representation for image search using self-supervised means. This is like quite a big, if you want to deconstruct it, look at maybe joint embedding representation, that's the how. Image search is the what. And using self-supervised means is how cool is this, right? Yeah, so, okay, let's see if we can move forward. Yeah, there we go. So a little bit about me before we start. I work for Elsevier Labs, like Charlie said. My title is Technology Research Director, although I actually don't direct anything or anybody. I'm basically an individual contributor in the areas of search, NLP, and ML. I used to be a search engineer, but nowadays most of my involvement is more towards the machine learning pipelines of search. So I kind of, I still work in search, but it's not really, I'm not in the forefront of search. It's more of, I try to find things that might help make it better. All right. So the talk, the way I have set it up at this point, is that I'll talk a little bit about the background to the problem. Then, and in this case, it's basically a deep learning model which is being used in search. So first I'll talk about the model, the fine-tuning aspects of it. Or, if you think about it, the ML part of it, and then there's the image search part of it, how do you deploy it in an image search pipeline. And finally, I want to show you two demos. And yeah, so we'll get to that. So if you think about, image search, without thinking of the vector search piece, right? You think about it and you say, how do I do image search? Typically, you might, or actually, this diagram is actually quite nice. So this is a Wikipedia, info box from the Scream. It's an expressionist painting, oil painting by Edward Munch, and it talks about the anxiety of the human condition. And so, and the middle piece, this text piece, is basically the abstract of the Wikipedia page, right? And on the right, you have what is known as the info box. So typically, you could think of, when you have an image and you want to search on it, you could take the abstract of it or the caption of it, right, and do a text search on it, because we already know how to do text search. Or you could run it through some kind of pipeline that Wikipedia has. It could also be some of your own, and extract extract tags out of the image, and then do a faceted search. Again, things that we know how to do, right? The other option, of course, is embeddings-based search, which I'm going to talk about. And the other, and that was one of the motivations, like, if we can get to an embeddings-based search with what we have. And the other thing was that it, ideally it should be unsupervised or self-supervised, because it's expensive to get people to, label data for you, right? So, talking about embeddings, so I'm not sure how, well, I guess word2vec must be at a, at least at a high level, you know what it is. So basically, that's kind of my, the origin of my understanding of the whole embeddings idea. And it will become, important as you understand, as I go forward. So I'm just going to cover this a little bit. So embeddings are based on the distributional hypothesis that words that are used in similar context tend to have similar meanings, right? And so, word2vec was the first one which kind of made this whole thing popular. where it basically ran against a big body of text, and it found words which were, used closer together, and it was projected into a low-dimensional, 300-dimensional space. And it turned out that, in this space, words that actually, were used in similar contexts were actually, clumped close together. Something like the image that you see here. Although this is, I think, more biblical than anything else. But anyway, so that's word2vec. But the nice thing is that this thing is not only for words. It also this kind of effect that we see extends also to images. So here are two examples. One from the unsupervised world. So these are the first one, the top thing here. These are from the MNIST dataset. So these are handwritten images of handwritten numbers, right, from 0 to 9, and these are used mostly nowadays in student things. It's kind of old, but what these guys did was they took these images, and it's like a grayscale image, so I think 14 by 14. So they took this whole pixel map, and they sent it through a sparse autoencoder to squeeze out the relevant pieces out of it, almost like what you do with word2vec, right? And then when they did dimensional reduction and projected on 2D, and you can see this kind of clustering, right? You can see all the 8s clustered together, all the 1s clustered together, and so on, right? So the whole point is that the embedding knows something that is interesting, right? And you can see the same effect with supervised images as well, supervised pipelines. So ImageNet was a big image competition to classify 1,000 images, and networks that did well we could now use them as encoders, right? Image encoders, by taking the head off. And so if you did that, you would find that you take a bunch of images and you pass it through that encoder. It was fairly easy with low amounts of training data to actually classify things. Like, so here you have this bunch of images of animals, and you pass it through the image encoder, and then you train it to classify dog or cat, right? It's easy to do. So there is something about these encodings that contain information about the image, right? So that's the point about the embedding here. So I'm going to shift a little bit to contrastive learning. So although embeddings are, they talk about embeddings in points in space, contrastive learning talks about pairs of images, right? And I want to go into contrastive learning because image search is really a ranking problem. So it's, image search is kind of image similarity, and you're basically saying, relevant results must appear above less relevant results. So it's a pairwise, a measure. And so contrastive learning is basically, it takes, so if you can look at this, the example here. So you have two images of Steph Curry, and the encodings for that ideally should, place them close together, these two images. Whereas if you have, say Steph Curry and somebody else here, in that case they should be further apart than images of Steph Curry himself, right? And so the idea here is that contrastive loss, and so again, contrastive learning uses contrastive loss, which we'll cover in the next slide, and it is better suited for ranked, this kind of pairwise ranking problem than classification loss. And so that's contrastive loss in general. And for a more mathy treatment here, so it's basically given a pair of terms, x0 and x1, and a label y, which is 1 if x0 and x1 are similar, and 0 if not. You are defining contrastive loss in these two, in this way. And so if y is 1, you're only this part is relevant. This part disappears, right? And vice versa. So for similar for similar pairs, you are trying to minimize the difference between x0 and x1. Whereas with dissimilar pairs, you are trying to minimize or maximize the difference, but using a margin, right? So here, this max thing means basically that you have, like, if you have a marginal loss of m, you don't spend any more resources in going forward. All right. So advantages of contrastive learning, again, no explicit labels. You just need to know what is similar and what is dissimilar. And hopefully you have some kind of hint from the natural world about this, right? So for example, in our case, we are publishers, right? So, and STEM publishers. So most of our images come with captions. So therefore, we can say that images and captions, they occur naturally in the wild for us, right? And tons of them. So, but again, and the idea here is that once you know about similar pairs, you can infer dissimilar pairs, anything which is not similar being dissimilar, right? And of course, pairs can be multimodal. In our case, it's images and captions. And you can see it here as well. I mean, there is a diagram with multimodal things, but again, this is not new. We just talked about this with the Steph Curry example. So the first input, and this was kind of the inspiration for this whole project, the convert paper, right? So the convert paper was pre-transformers. It was trained on medical images and captions, again, self-supervised. They used radiological x-rays and radiologist nodes, associated radiologist nodes. Again, things that occur in the wild, right? So essentially, it's a Siamese network. You have two towers. One is the text encoder, and one is the image encoder on the top and the text encoder on the bottom. The image encoder is the ResNet 50 from the ImageNet days. It's a pre-trained ResNet 50. And the text encoder is BERT. So not truly pre-transformer, but really at the border when BERT had just come in and become the de facto encoder of choice at that point, right? So essentially what it does, it minimizes the bidirectional loss between the positive image text pairs, right? So you have these two, and it's basically just a Siamese network with a slightly complicated or complex function at the top, the comparison function at the top. And so what you can see with that, and the convert paper showed that, is that once you train convert and you have this model, you can use that as an image encoder, and an image encoder that which is trained, or images encoded using convert do better on downstream tasks than images that were not encoded. And you can see this in the plot that they have shown here. This is the output of the data from the ImageNet directly, and this is after being passed through, encoded through convert. And you can see there's slightly more separation. Unfortunately, convert was not like, it didn't do really well. It did well, but it didn't do well enough to, for us to go further, right? So it sat there for a while. And then, so I also participate in some external groups. One of them is the This Week in Machine Learning podcast, and they have a Slack channel and people who come together to do self-learning and so forth. And so one of the things that we did as a group there was that Hugging Face came out with a community event. They were trying to promote their JAX models. JAX is like a linear algebra package like TensorFlow, differentiable. And coincidentally, the compilation step that it uses works very well with TPUs. So what Hugging Face was offering was that we take one of their JAX models, and they give us free TPU time to train this model to do whatever we want with it. And that was the competition, right? So a bunch of us joined in, and I had been talking about this convert idea for a while. So somebody said, like, let's do CLIP. And so I didn't know about CLIP at that time. This is the first time I learned about CLIP, which was nice. So and we initially tried, wanted to do medical images, keep the exact thing going. But there was another team which was quicker, and so we said, okay, we'll do satellite images instead, right? And we actually ended up placing third, so which was nice. So in any case, I have a blog post here in case you want to read more. This image I included here. I'm going to show it in the demo, right? So there is a reason I included it here. Okay, right. All right. So let's move on to the next piece where we basically do the model fine-tuning. So the base model that we used was OpenAI CLIP, and CLIP stands for Contrastive Language Image Pre-training. And obviously, in the tradition of all pre-trained models, it is trained on massive amounts of data, 400 million image caption pairs from the internet. The training time was 256 GPUs for 2 weeks, and OpenAI paid for that, and they made it available for everyone to use. So that's what we started with. So the OpenAI CLIP at that point matches ResNet 50 performance. So ResNet 50 was trained in a supervised manner on ImageNet, right? This one, using self-supervision, matches the same, gives you the same performance, right? So some indication of how powerful it is. And it's actually, it gives you good performance on natural images, right? The stuff that is trained on, it actually does quite well. And if you remember Convert, we used to have a text encoder and image encoder. This is all fully transformers, so both the text encoder and the image encoder are basically transformer architectures. And the nice thing here is that it's all available on Hugging Face. And that's actually a big deal, at least it was a big deal for us, because we were able to leverage the stuff that people have already done. And so we had comparatively much less to do, right, as a team in both the projects that I'm going to talk about. So essentially, fine-tuning is, we did batch-oriented contrastive learning. So, as before, we have 2 towers, right? So one tower which is doing the image encoders. So let's say you have a batch of size n. So you have n images, and then the captions, the captions corresponding to those images. So n captions. And then this goes in as this huge batch size of n by n, right? With everything along the diagonal are positive pairs. So you got n positive pairs, and everything off diagonal are negative pairs. So n square minus n negative pairs. So you don't actually use all of them. CLIP decides how much to sample from that. But essentially what you're doing is that you're using all the positive pairs, and you're sampling from this pool of negative pairs. And it uses, so we didn't change any objectives. So we reused the CLIP, so its own objectives. We reused their sampling strategy and everything. And so our idea was basically that we just gave it image caption pairs from our own domain in both cases. So in the first case, we did satellite images with captions, and in the next one, we did medical images with captions. All right, so talking about the medical part. So the data set was, again, an external one. So there is a caption prediction task from ImageClef 2017, where the idea was that they would give you an image, and you have to predict the caption. So they gave us this data set, which is quite nice. I mean, 164,000 training images and 10,000 validation images with captions. And then they had 10,000 images without captions for which you had to predict the captions. We didn't care about prediction because we didn't want to predict captions, so we basically repurposed the first 2 splits, and we used it for fine-tuning our medical images and captions. And so essentially, we ignored the provided test split, split the training data set 90-10, and this is the splits we end up with. And so, talking about evaluations, so before we started, we wanted to baseline our model to see how good or how bad it was. In this project, we chose MRR at k. And in the satellite project, we chose recall at k. So we wanted to be a little more stringent this time. So not only do we care that your correct caption occurs in the top k results for your image input, you also care that it is in the top position or not, right? So if it's not in the top position, you penalize it accordingly. So that's why we used MRR here. And as you can see, the baseline with the baseline with our medical images is basically saying that the correct caption is returned about 43% of the time, and in the first position, and 57% of the time within the first 10 positions. So it's not so great. And that is kind of understandable because it is trained on images that you can see, right? this is stuff that is inside. You have to cut me open to see it, right? Or you have to put me under magnification to see it. So it's not things that it would normally expect to learn about. All right. So, and this is more of the model training bit. Again, I don't know if this audience cares about this, but you probably would if you were to replicate it. So what we did was, we tried various parameters for different parameters for our training, different training runs. And so the one that worked best for us is this, right? This set of things here. And we used, and there's a slight difference between the way we used regularization in the satellite case versus this. In the satellite case, we actually had a lot of compute. We had TPUs, and it was like really fast compared to what I've done with GPUs here. So we were able to go through much larger data slices, and so we actually ended up augmenting our text and images in both the text and the images. Whereas here, not only did we not augment, we actually did random sampling. So instead of using the 148,000 training data set for the training, we would use batches of 50K samples from that, random samples from that. And yeah, so as you can see that it still resulted in a pretty nice loss curve, and at this point the training loss is still falling, but the validation loss is kind of flattening out. So we felt that it was a good time to stop, right, and move forward with actually using it. And so here you can see the results, and we did 5 different runs, and you can see the difference between the baseline and what we got here. So right now MRR at 1 is about 0.8. and MRR at 10 is about 0.87, right? So much better than what we had previously, right? Okay, so, all right, okay. And so once we have this, once we have the fine-tuned model, we did, so this is the kind of architecture that we use for the image search bit. So first off, we took all our images, including the ones that we dropped from, because we didn't have captions. So we took all of that and encoded it with this fine-tuned model, and we L2 normalized the images on the way in. The reason for it is because we wanted to do cosine similarity, and cosine similarity, if you recall the formula, it's basically a dot product with the normalization constants in the bottom, right? And it is cheaper to do dot product and not normalize each time. So what we wanted it to be bounded between 0 and 1 because it's easy to understand. So we figured that we might as well take the pain and L2 normalize on the way in, and then everything is nice and L2 normalized, so you just do dot product and you get cosine similarity, right? So it's just a thing that we did, and okay. So any case, the encoded image vectors are put into a vector store. And at query time, the query text or the query image is encoded using the same fine-tuned model to create a vector. And then the vector store is searched, right, for encodings that are close to the query vector. And then the top K search results are basically the images and caption that correspond to the top K closest vectors returned in the query results. And so again, vector search can, initially we tried exhaustive search, and that took a long time because essentially it becomes like a naive vector search basically means that you take the query and you map it or you compare it with every element in the corpus, right? Every vector in the corpus. And we didn't try it for this one. We tried it before in smaller cases. And we basically came to the conclusion that it's not going to work for us. So in case of the satellite image, the vector store that we had was FICE, which supports approximate nearest neighbors, but it's all in memory. And in this case, it was Vespa, also supports approximate nearest neighbors, but not in memory, but this is all in like a database now. So we have different, so I wrote up a little bit of different kinds of approximate neighbors. The one we are using is HNSW. And there is a blog post by James Briggs, the Pinecone, who's done a real good job on explaining these things. So I'm going to try and leave it here. So, and the other space partitioning are basically, you try to cut the space up so that you have to search fewer, subparts of the space, right? So that's basically all it is. And HNSW works a little differently. It basically says, okay, I want to look at these nodes, and then I want to take these nodes and look at the subset of nodes bounded by these nodes, and so on, right? But read the blog post. You'll basically find more information there. And so we chose Vespa as our vector store. Again, I don't work for Vespa, but a big fan. It's a hybrid search platform. Supports both text BM25 and vector. It does more than HNSW, but I'm just using HNSW here, and just to allow easy comparison, before and after kind of thing. So our demo application allows you to do text to image search using straight caption text, matching on caption text, matching on the caption vector, matching on the image vector, and a hybrid of that. And there is also another one which image to image search. So I give you I select one of the images from my output and basically say show me all similar images, right? And I can do it with images and image and caption as well. Again, I mean, just to show you, Vespa, Vespa has a high or very steep learning curve, but Vespa CLI has done a lot to make it easier, and so basically, but regardless of what you are going to do, what dataset or indexing platform you're going to use, you're going to have to specify a schema. So this is my schema to Vespa. And as you can see that the image ID and image path are basically just for pointing back and getting back the image in my search results. The caption text is indexable, so I should be able to search on the text, BM25 search, and the clip vector is a 512 sized float array, and it is indexable and accessible using HNSW. So that's what I'm basically saying here, right? And then I have to create rank profiles. And so I have 3 rank profiles. One is a text-based search, which is BM25 of caption text, and image search, which is a closeness, which is basically dot product of some field I supply and the clip vector. And I will have to define my clip at some point. And a combined search, which is here, in my case, just a linear combination of the 2 above searches. I could make it weighted. I could say 0.5 of this or 0.3 of this and 0.7 of that and so forth, right? So when I did this, this was like I used a bunch of homegrown scripts. I kind of extrapolated from Solr and said, what do I need to do in Solr to make it go up and down and do stuff with it? And can I do the same thing with Vespa, right? So I built a bunch of scripts and did that. But I think a better way to do it now is using the official scripts at Vespa CLI. And now it's time for the demos. So I'm going to show you 2 demos of demos of 2 systems, right? The first system is going to be the medical image search platform that I talked about, the medical image search application. And the second one is going to be the satellite image search application. Right? There is some additional functionality in there, which I would like to show you and, kind of invite you to think how it would be, how applicable it would be in the medical field as well, right? So in any case, let's start with the medical application. So the first, basically, my search application, this is written using Streamlit and with Vespa in the backend. And it has 2 major pieces of functionality. It's like the text to image search and the image to image search. So for the text to image search is just like regular Google. There is a search box. You type in a string, and it finds you images that are close to that string, right? So images that are relevant for that string. So let's start with this. So we have let's say we started with a general high-level query, right? So we say computed tomography, right? And then we do a text search. Now, with a text search, basically all it does is it does a BM25 matching with the caption text, right? And and so as you can see here, you asked for computed tomography, and it does have computed tomography in here, right? And if you go further down, there's another one here, right? and so on, right? So my point is that it is matching the caption text, right? Now, what happens when you do a vector search, right? So when you do a vector search, it basically, what we do is we take the embedding of the string computer tomography using the fine-tuned model. We get the embedding vector for that and find the images which are nearest neighbors of that embedding vector, right? Whose vectors are nearest, closest to this query vector, right? And as you can see, when we did, vector search, we basically have, so the first one does have computer tomography in the caption, but the second one doesn't, right? So this was part of our test set, which did not have any captions, which we also included in our corpus for image search purposes. And as you can see, the image does look like computer tomography, but there is no hint from the caption that it can use, right? Similarly, if you look at the third one, it says CT coronal sections. CT is an abbreviation for computer tomography, and but the system doesn't actually know this, right? So it basically depended on the the nearest neighbor piece, right, where the closeness of the clip, the effectiveness of the clip embeddings, right, to basically find give you images that are computer tomography images, right? And similarly, you can also do a combined search. So combined search is just it computes the score of the BM25 search and computes the score of the HNSW search, and then it combines the two in some way. So I did not do much work on it. I basically just add it up, but you could of course do interpolate in different ways, right? Weight each the text side and the vector side in different ways. So maybe 0.3 of one and 0.7 of the other and so forth, right? But again, I haven't done much work on that, right? So I'm not going to go very deep. The results are not that much different from text search. The results are slightly better than text search. And so you get the massive recall of text search, but not so much, but maybe slightly better quality, right? So that's maybe all it is. So we could now drill down a little bit. So you can say computer tomography of, say, brain, right? And then text search we already know how to do. So let's look at the vector search. And then you see here it says CT scan of the head. So it has figured out that the head and brain are kind of similar. CT is computer tomography. Again, we have this no caption provided situation where it actually found what it found, right? Found what you asked for. And then it says pediatric brain CT scan series. So again, so my point is that even though the caption may not match, or even though it has no other hint from text, it can still find images based on its understanding of the image space that it learned, right? The embedding learns, learns the image space basically. So it is able to find you, similar images like this. Okay. So let's try something else here. So maybe we say gram. This is from pathology, right? So we try gram-negative stain. We do a text search just for kicks. And well, there is nothing in my corpus which says gram-negative stain. Now, if I do a vector search, I get 10 matches. And the first one, nocardia organisms, I'm not really sure what this is, but but if you look at the second one, it says the ZN staining, right? Now, ZN staining happens to be a related method similar to gram staining, but not exactly the same. So it actually found, so I believe the only difference is that ZN staining uses heat as part of its process and gram staining does not, right? And you find results for gram staining, not gram negative stains, right? So, so it did give you, similar images. And again, how much is relevance and how much, so again, the balance between precision and recall, this is something that has to be figured out. There is issues here. So in any case, so now that we know that we have gram staining here, I want to find other images like this, right? So to do this, I could basically take this ID here, and I could do image-to-image search, right? And I could do something like this and say, just search using the image.
and I could get other gram-negative or gram-stained images, right? So obviously it found itself, and the relevance is 1. But then it also found other ones which are similar, right? So if you look at the top 3, they're all gram stains, right? So, again, it does, bring back relevant images, right? So, okay, enough of this. So let's actually go to the next one. So here I want to show you this find features in image thing. So retrieve images given text and retrieve images given image is basically the same thing that we saw in the previous demo. But here, this is a little different. So what it does is if you pass in an image, it cuts it up into little pieces, and then you can say that, show me pieces of this image or areas of this image where this object is found, right? So it's like find some particular feature in the image, right? So in this case, for instance, if I do beach, right? So this image is of a port, right? And so let's say if I do boats, for instance, right? So there's lots of boats here. So if I do that, and I do a find, oops. Oh, okay, sorry, I did not select, sorry. So if I do boat, and then if I do a find, let me do it again. So if I do a find, it will basically compute the probability of finding a boat in different pieces of the image. So and it basically ranks them as well, right? So if you look here at the bottom, it says this is the number 1 patch, which contains boats, and the probability of finding a boat is 0.46. And this is the number 2 patch with probability 0.170, and this is the number 3 patch, probability 132, and so on, right? Similarly, you can do other images, right? So there is another one which I wanted to show you here. And so this is a forest with a river. And so let's look at trees. Forests have trees, right? So let's look at trees. And you do a find. And as you can see, there. Takes a while to come back. Okay, so as you can see, this one says it's number 1, this one says number 2, but there's lots of trees. It's kind of hard to figure out, right? So let's do river, right? So it should show me the river, right? The blocks that contain the river. So let's look at this, and it says which one is number 1. So this is number 1. It has quite a bit of river in it. This is number 2. This is number 3. This is number 4, 5, and 6. So it has essentially traced the path of the river in the image, right? So how does it translate into medicine, right, or medical images? It could, if you think of radiology, and if you think of this as being a digital assistant, it could find suspicious areas in the the X-ray or whatever image is being analyzed, right? It could find suspicious areas and highlight it for the human radiologist, right? So at least, it's like a digital assistant. It can lessen people's work. So in that sense, I thought it would be, useful to show here. And I think that's pretty much all I had. So I'm going to stop here.
These are the links here. Sorry, I should go back to. And finally, in the interests of reproducibility, I have my code. The code I did for the image-caption project is open source now. The old one, the one on satellites, that is open source by default because it was Hugging Face, and we did it as a community event. Yeah, so, and the blog post has links to that in case you feel like looking at it. And that's it. I can take questions, and yeah.
Okay, so I don't know how to phrase the question, but I guess if you're ranking different search results based on the cosine similarity, have you tried any other ways to rank the things given your 2 vectors? Any other types of scoring methods?
We have tried Euclidean distance as well. Cosine similarity seems to work most of the time. Euclidean distance also works, but in some cases Euclidean distance works better. Not for image search though, but for other vector searches. There was this one time I think we were extracting keywords, and for that Euclidean distance worked much better than cosine search. But for this we have mostly, in both cases we have used cosine similarity, and that worked nice for us. Well, one reason is because FAIS and Vespa both support dot product, right? So you are kind of constrained by what is offered. But when you can do your own, yeah, you do try different ones.
Okay, thank you. So we're going to try something here. I'm going to ask a question that's been submitted by our online participants. It's amazing this is working. Shantanu Ladwi said, what is the loss function used in CLIP?
Oh, it's this contrastive loss that CLIP has its own contrastive loss. It's a contrastive loss, which I'm not sure exactly what it is, but it's the one that's used by CLIP. We didn't make any changes, which is, yeah.
Okay, thank you.
Yeah.
So we have a question up here.
So I have a two-part question. The first question is just a little more mechanical. I was just curious, did you use PyTorch or TensorFlow?
PyTorch.
PyTorch. The more meaningful question is, have you thought about, so you're doing images with text. Have you thought about actually modeling the topics of the text to be informative of the picture? Right, because you look at your results, you're looking at it, you're just doing a relevance score, and you're looking at images, and you're trying to rationalize what am I seeing, what's going on, and your only metric is relevance, is sort of a comparative off cosine. But if you actually modeled the topics that were occurring within the space and then searched that topic space, you'd have a beautiful descriptive nature of what the model understands.
Yeah, possibly, yeah.
Food for thought.
Absolutely, yeah. Also, we did, the image-caption one. That used PyTorch. The other one, the satellite, that used JAX. Yeah.
Okay, thank you. So we now have another question from the online group. Jack Mazan asks, for combined search, how did you control influence on score between distance score and BM25 score?
Yeah, that's the thing I said, right? I just added the two. And the fact that you can add it was the cool thing for me. I didn't actually play around with the numbers to see whether I could. And really, I mean, the combined score didn't do very well for at least at the level of effort I put into it. I just added the two numbers. Right, so.
Thank you. So do we have any more questions from the audience? Okay, while you think, I've got another one from online, from Shantanu again. How much time or resources were required for fine-tuning the CLIP model?
Oh, how much time?
Yeah.
The first one was, I think we took 10 days, group of 5 of us. And there was division of responsibility. So in the first one, in fact, I didn't do any fine-tuning. I did most of the front-end work, right? The demo, and then I helped out with the image augmentation and so forth. But in the second one, it was all mine. So the second one was actually a dev 10. So we have, the company gives you 10 days to do your stuff, do whatever you want, and come up with something. So this was mine. So this took me, they gave me 10 days. So this took 10 days, right? Or less, maybe, too. Yeah.
Fantastic, thank you. So last chance for a question from the audience. And we've gone through all our questions online. Thank you for that, our online people. So thank you very much, Sujit.
All right, thank you. Yeah.